Okay, hello and welcome everybody to a class that I am tentatively calling Pre-Quantum Mechanics. Because really what you want to think is maybe if you've taken algebra and then you first took pre-algebra, you've taken calculus, you first took pre-calculus, we're really trying to set you up in this course for all the math you're going to need to have a very sound understanding of quantum mechanics. We're not going to skip over anything so that you won't feel prepared for a quantum mechanics course. To that end, as far as maybe a math department would be concerned, this course is primarily linear algebra with pieces of differential equations. And if you're curious about maybe what is linear algebra, because it sounds kind of easy when we use that word algebra, in reality every time a mathematician uses the word algebra, what they actually mean is a mathematical structure, endowed with a multiplication. Okay, and this multiplication can be incredibly abstract. This is why some people refer to abstract algebra as a course as well. Linear algebra is not too bad. The multiplication is a multiplication corresponding to linear maps. And so what a lot of mathematicians interpret linear algebra as is the algebra, that is to say, a structure endowed with a multiplication. So the algebra of linear maps on finite dimensional vector spaces. And in this case, in all sorts of non-trivial settings, when I use the word finite dimensional, what I actually mean is that the dimension is strictly greater than 1. Because when we work in a one-dimensional vector space, things get fairly easy. So in some ways, linear algebra is everybody's first experience with a higher dimensional vector space. I mean, sometimes in Calculus 3, depending on if you take Calculus 3 first, you've experienced it there too. But depending on where you are, you may take Calculus 3 before or after linear algebra. And that's really what linear algebra is. So we're thinking about higher dimensional spaces, and we're looking at the algebra of linear maps on those spaces. Now, differential equations, let's describe what these are really quick, even though they're going to play a smaller role in our semester. Differential equations are equations, aka qualities, or an equation is really an equality containing an unknown, where the unknown, number one, is a function. Okay, so that is to say that these are functional equations. And secondarily, has at least one derivative of the unknown. Could have much more than one derivative of the unknown, but you have to contain at least one, and then you're a differential equation. And really the way you would solve a differential equation is the same way you solve any other equation. You're searching for the unknown. And so this semester we're going to cover, it's going to feel very similar to maybe a standard linear algebra course, the sort of linear algebra courses that would normally be offered by a math department, but we maybe can't get into a couple details there, and instead, to get away with us taking time off of linear algebra, we go into differential equations just a little bit, just so that we understand what's going on in quantum mechanics. So to that end, let's just very quickly analyze the primary object of quantum mechanics, and likewise this course. So we're going to refer to this object basically as much as we can. You've probably heard about it. This is the Schrodinger equation, if I can spell. Schrodinger equation. And in fact, we're going to be working with the time-dependent Schrodinger equation. So the time-dependent Schrodinger equation looks like the following. d dt of, this is the Greek letter psi, and it's surrounded by something called a ket. So those angled brackets, well, it's flat on the left and angled on the right, that's called a ket. This is the Greek letter psi, psi, inside of a ket. We won't refer to kets too often in this course, and honestly, psi we won't refer to too often either. But just in case you're curious what the names of all these things are, you're taking a derivative of this object, which is psi inside of a ket, and it's set equal to h, and oftentimes h has been given a hat, and that acts on psi inside of a ket as well. I am forgetting a couple small terms. There's an I and an h bar sitting out front. So the I is the imaginary number, which satisfies I squared is -1, and the h is the quote-unquote normalized Planck's constant, those two terms really don't play a huge role in what goes on with Schrodinger's equation. In reality, the terms that play really big roles in Schrodinger's equation are these psi's, and we should talk about what those are. Mathematically speaking, these are vectors. Okay, so mathematicians have this word vector, but you don't want to necessarily associate that word to maybe what you've experienced in physics or other math courses so far. They're vectors in a very abstract sense, okay? So I'm going to write that here abstractly, and we'll encounter what it means for vectors to exist abstractly later. Quantum mechanically, these are states. So that's really the same thing between, mathematically or quantum mechanically, the difference between vectors and states. But when we go through this class, we really are going to think of them as vectors, because that's really where all the math comes from, is the math of vector spaces. And this is what you've already been able to see up here. This is why we're going to be analyzing vector spaces. It's because vectors are the fundamental objects of quantum mechanics. They are representatives of the quantum states. And then this object H over here is what's known as a Hermitian operator. An operator is a vague word that we'll get into eventually that has a notion of existing in either infinite or finitely many dimensions. When it exists in finitely many dimensions, which is the cases we will encounter often, these are going to be known as matrices. And matrices are always associated to these linear maps on finite dimensional vector spaces. So that's really where everything's going full circle, is we really care about this object H, or H hat, as a Hermitian matrix, which is just as fundamental of an object in linear algebra as the vectors that they act on are. And then we're going to be analyzing vectors and vector properties as well. And then certainly we have ourselves a lovely ddt there, which is the time derivative. And hence the Schrodinger equation is a differential equation. And so in just analyzing the Schrodinger equation alone, we can actually see why the math of linear algebra and differential equations really is the math of pre-quantum mechanics. This is the math that needed to be developed before any sort of quantum mechanical understandings can be constructed. So we're just going to kind of stare at that and use it as our go-to example every time we encounter a new object this semester. But in reality, we need to take so many steps back, right? Because I think even listening to me right now, you're maybe getting a little bit timid, things feel a little bit scary. They shouldn't be. So we're going to jump all the way back to the beginning, and we'll work through all of this in general until we get to the end of the semester, and then we'll be able to analyze this Schrodinger equation in some explicit detail. So to that end, let's move forward in what I was saying with introduction, sets, maps, and functions, and make our way over to sets. Now, unfortunately, the rest of this video, even though I said the earlier part was scarier, I kind of still agree with that, but this later part is going to be slightly intimidating in terms of memorization. So I can't stress enough, you basically need to memorize the rest of everything I say in this video before we move forward, and that's just because we're going to be referring back to it verbally the entire semester, and if you don't know what I mean, every time I use a word, you're going to have a really hard time understanding what I'm saying. It's almost like a new language. So you're almost trying to teach yourself a new language really quick before we move onwards so that you actually know the language I'm speaking. Sets. A set has a definition. A set is a collection of mathematical objects. I don't put mathematical in quotes here because a mathematician, almost any object or idea is a mathematical object. So really it's a collection of hardly, basically anything. So it's a collection of mathematical objects denoted by curly brackets. And these curly brackets, I'll do my best to draw them. I don't know how good you are at drawing them either. You get better the more you practice. So we have these curly brackets, and they define sets. And so you can just put a collection of objects inside of curly brackets, and that's going to define a set for you. Now that's very abstract. Unfortunately, there's not too much more to the definition than that, so you just kind of have to be okay with placing objects inside of curly brackets and calling that a set. But to this end, there's something called set builder notation. So set builder notation is an incredibly useful notation for basically what you can get away with is using sets to define future sets. So set builder notation allows us to use, I'll say, easy sets to define harder sets. And the way set builder notation works is you're going to have your curly brackets, let's say denoted by, you have a curly bracket. On the left, you have a collection of objects from a set, And then there's always a vertical line, and then you'll end up with something else to the right of the vertical line, which is properties the objects must satisfy. And so the way we often read set builder notation is we read from left to right. We say we have a collection of objects, and we read this vertical line as such that, or satisfying, because everything on the right-hand side is then a collection of properties that get satisfied. Okay, so I can just define these, but that doesn't mean that we have a good understanding of what they actually are. Let's look at some examples. So in this course, I'll use e.g. for example. That's Latin. And a great example of a set would just be the natural numbers, which is often denoted by n with a double stroke on the left-hand side. And there you can tell I'm using my curly bracket. I place a 1 in there, and then a comma, and then a 2, a comma, a 3, a comma, a 4, a comma, and then I use dots, and I realize that's maybe a little bit vague. And mathematicians are surprisingly vague sometimes when we describe sets. So we just have to be okay using our context clues to make sure that we understand sets correctly, but it's 1, 2, 3, 4, and so on. You can think about all of these as the positive whole numbers. These are called the natural numbers. And that one I've just kind of defined as a set nice and explicitly. But what we can get away with, now that we have set builder notation at our disposal, is maybe or maybe not, you know this, the z with a double stroke down the diagonal is known as the integers, and these are all positive and negative natural numbers, including 0. So I can definitely denote these in some sort of non-set builder notation context. That would just be me trying to describe the set explicitly, but I can also use a set builder notation here. And I can use set builder notation by referring back to n. So I can refer to n to construct z. And that's because of what I just said explicitly. It's the positive and negative natural numbers and 0. So how do I get away with this? I can say I have positive natural numbers, I have negative natural numbers, and I have 0, such that n and n come from the natural numbers. So I've used a new notation here. This is a notation directly read as element of. So it kind of looks like an E, but it's really like, I usually write it as a C and then I place a horizontal stroke in the middle. You read it as element of or belongs to. It just means that we're placing this n here inside of, from the bigger n. So that means that we're taking each of these n's from the natural numbers. That's how set builder notation can give me all of these, because I take all natural numbers, all negative natural numbers, and 0, and I end up with the integers. So that's like the first example of set builder notation, the integers. And we can actually move onwards. So I'm going to construct some of our mathematicians' favorite sets, which all happen to be numbers. So if I move onwards, I can construct Q, where Q also has some double strokes on the left and the right. Q is going to be all fractions. And I'll just write this in English. It's actually perfectly valid to use English inside of curly brackets for sets. So I can say all fractions of integers. But if I wanted to use set builder notation, I can actually get away with that, right? Because Q divided by P such that Q is in the integers and P is in the integers and P is not equal to 0, right? Because I wouldn't want to divide by 0. I wouldn't want to accidentally place one of those into my set. But that's another example of set builder notation where you can just construct a new set using some of your older sets. So it's really cool. What have we done here is we started with n, and then we used n to construct z, and then we used z to construct q. So it's really quite interesting that you can get away with all of this with set builder notation. So I'll give q a name. I did already refer to it as the rationals. And then finally, we also have r, which is going to be, let's just use it in English first, all limits of rationals. If I want to use set builder notation here, I can say it's the limit of a sequence of rationals as n tends to infinity, given that each of Qn are a rational number. These are the real numbers. And I suppose I should probably cover the complex numbers. That's really the topic for the next section of our course, but let's talk about it here. What are the complex numbers? These are the easiest ones to simply define straight from the reals using set builder notation. We often define them as x plus iy, such that x and y are in the real numbers, and I squared has been defined to give me -1. These are the complex numbers. As far as this course is concerned, the naturals, integers, reals, and complex will all be very, very important. The rational numbers will not be too terribly important. But certainly these reals and complex are going to be incredibly important for us. So I will refer to R and C all of the time. This is a good example of using set builder notation. I do want to comment, let's just do one more example, where I'm not even going to use set builder notation, but I do want to comment that sets, even though all of these examples I provided for you are numbers, sets definitely do not have to be numbers or contain numbers. So we could just have the set which consists of planes, an airplane, or something. You could have trains, and you could have automobiles. That's a perfectly valid set. Even the set of those three symbols, the symbol of a plane, a train, and an automobile. So we can be as abstract as we want with what we place inside of sets. It just so happens that numbers are the useful objects to place inside of sets. They just have natural operations associated with them. You can make true or false statements a lot more easily when you're working with numbers. So in general, we're only going to really see sets as numbers, except for the one case when quantum mechanical states are not numbers, and yet they are still very real mathematical objects. So we saw earlier that this psi placed inside of a ket was a quantum state. It turns out that we'll want a lot of quantum states to be grouped together, and we often will enumerate these psis with some subscripts 1, 2, and 3, etc. These states will be grouped together into a set called, the quantum states. And they don't have like kind of a real world instantiation as a number. What they often refer to is measurement itself. So, when people refer to an electron spin as being spin up or spin down, there's not really a number associated with that spin. It's the notion of up or downness that can be measured. That is the quantum state. So we have to be okay with just working with ideas inside of sets. And in fact, they behave as vectors. And we'll take our time before we get there. But an up, whatever upness is that we associate to an electron, spin upness, that will behave as a vector mathematically. And there really isn't a number associated with it. It just is upness itself. So we do eventually have to get okay with not necessarily seeing numbers in all of our sets, even though those tend to be the really, really useful sets. Finally, one last example I do want to cover when it comes to sets, because this is something we will use quite often, is interval notation, where we use a square bracket, and then we take a single real number, and then a second real number. And you'll notice this semester I like to use subscripts all the time to enumerate objects. But square bracket, real number, and then another real number, and then close the square bracket. This is going to be a set. So interval notation is a way of talking about sets of real numbers, where this is actually the set of all real numbers. So let's just call it x in R. So they're all real numbers satisfying something in particular. What does it satisfy? It satisfies that the x is greater than or equal to x0 or less than or equal to x1. And we have a couple other notions here. We can go with both open brackets, where once again with my set builder notation, with open brackets I use no equality on the inequalities. And I can do both versions of the open brackets as well. Nothing needs to be completely open or completely closed. So this would be x0 is less than or equal to x is less than x1. And finally, the set of x in R satisfying that x0 is strictly less than x, which is less than or equal to x1. And so we refer to the square brackets as closed brackets, and we refer to the parentheses as open brackets. We can also refer to them as parentheses sometimes. And they directly correspond to whether or not I'm using the equal sign included on the inequality or no equal sign on the inequality. And you've probably experienced this before in your pre-calculus courses, but I just wanted to refer back to set builder notation. That interval notation really is directly related to set builder notation. So moving on to functions, let's say both maps and functions, because they are actually the same object. It's just that a lot of set theorists This is a specific subset of mathematicians. Set theorists like to use the word map sometimes, where basically everybody else calls things functions. Some people like to refer to functions as only operations on number systems. So the input and the output are both numbers, in which case you could say something like these planes, trains, and automobile sets aren't included in function sets or in function domains, but I think that's a little bit too restrictive. So in general, we're going to say that these are the same. We'll say same as maps. Okay, so for our intents and purposes, I will just call things functions when I can, and you'll see me refer to some objects as maps as well, and just keep in mind the whole time that they're the same object. Maps and functions are the same thing. Okay, to that end, what is a map or a function? A map or function is an assignment. It's a rule, technically. A rule, domain, and codomain. Now, we don't know what those are yet, but it's a rule, domain, and codomain, where the rule assigns a unique element of the domain, an element, instead of it should be each unique element of the domain, an element of the codomain. The element of the codomain does not have to be unique here, so that's why I used unique in only one point here. So it's denoted, I'll give it another line here, a map is denoted by a letter, a colon, a set, an arrow, and another set. For example, F colon R arrow C. The way we interpret when a map is defined like this is the F out front is the name of the map. So we can give maps names. The colon is basically meaningless. It just separates the name of the map from the domain and the codomain. And the domain and the codomain are always going to be sets. Set, set. So domain and codomain are always sets. This is why you have to cover sets before you can cover functions. And then once you have functions, they're given a name, which is a letter, and then they are given a codomain and a domain. Now, this may contrast with how you've experienced functions in the past. This is kind of more the mathematician's view of the function and not the high school math teacher's view of the function. If they are mathematicians, don't get me wrong, but there's just like a different view of what it means to be a function. A lot of times in the past, you were asked to find domains of functions. In reality, domains of functions should be given to you explicitly. Okay, so this contrasts with what you've experienced in the past. You were asked to find domains. This is where you'd be searching for dividing by zero or square roots of negative numbers or something like that. And you say, oh, those aren't in the domain. In reality, the domain should always be given to you. Now, whether or not you want to see it that way is up to you. And then you probably also worked with the word range instead of codomain. The range is not necessarily the codomain. The range is actually the subset of the codomain which the function reaches. So the codomain is allowed to be larger than the range. So codomain is a possibly larger set. And once again, given to you. So the function is already provided with its codomain. It's possibly a larger set given to you than the range. So I realize this contrasts a little bit with how everything existed in the past for you, but it's, I believe in all of you to be able to move forward. I haven't quite finished kind of this example. So I say a map is denoted by a letter, a colon, a set, an arrow, and another set, as well as its rule. Okay, so the rule then turns around and it says, what does the actual map look like? And the rule is always going to be this version where you place a variable from the domain into the function. So this is me placing x in the domain into the function. And then there's an equality which defines the rule. So for example, you've seen things like this, x squared plus 1. So both of these terms together define a function. So you can't get away with, in the past, right, high school math, I think, you kind of got away with calling that object the function, which it's okay. I mean, I'm not going to be mad at anybody if they define that as the function, but that's really only the rule half of the function. where you also have this notion of assigning the function a domain and codomain. So this is domain, codomain, assignment. So it's all of these together that really define a function for you. Let's go ahead and look at a couple of these examples. I think examples are always great for functions. So a really good one, f going from r to r, defined by f of x is x cubed minus 2x squared plus cosine of the square root of x squared plus 1 minus e to the x, let's say. Cool, there's an example of a function. We could also have g. Maybe it maps the complex numbers into the integers. Well, that's a spooky one. And maybe g is given by g of z is equal to the real part of z, and then the ceiling function around that. Now, I know a lot of you probably don't know what that means. Don't worry about it. That is a valid function from z to z. You could go h maybe from the natural numbers into the set of planes, trains, and automobiles, given by h of 1 equals planes and h of anything else equals trains. So once again, I realize this is a little bit of a contrived example, but there's a nice little piecewise function for you where you have planes and trains as your output. So there's just examples of functions, right? We want to get okay realizing that functions are kind of these rules as well as their domains and codomains. And let's actually look up again right here. Notice this C here I defined as a codomain. You'll see that actually nothing in the output was an element to the complex number. So if I square a number and I add 1 to it, I will still get a real number. So that's an example where the range is a strict subset of the codomain. But as long as whatever shows up out of the function is at least inside of the later set, which is the codomain, then we're okay with everything. So you just have to check that everything, like over here, the output and the output were definitely actually elements of the codomain. And just verify that everything that can possibly be output is an element of the codomain. And in fact, the poor automobile never saw a friend. And he doesn't have to see a friend. The whole codomain does not have to be met. You can definitely meet a subset of the codomain. So those are examples of functions. And we do have some other special words that we can use with functions that I'm going to cover, and then I'll finish this video, and we can kind of spend the next video on a lot more examples. Okay, so what are these final couple words? So let's say a couple terms for functions. We have something called injective, or one-to-one, or one-to-one. All of these mean the same thing. And what they mean, they have a very strict definition. It's kind of a difficult definition for a lot of undergraduates to work with. The definition of injective is that f of one input, so let's say f of x, right? That's the image of the element x, equals f of y, requires that x equals y. That means that if two things end up in the same place, I'm requiring that they started in the same place. So that's what injective means. Maybe I'll write what I just said in person. If two objects end up in the same place, then they must have started in the same place. No roads are converging here. We have something called surjective, or onto. And this is just the case when the codomain and range are equal. Now, I haven't defined range for you yet, so let's define range really quick. The range is the set or collection of all outputs. So you just combine all of the outputs of the function into a set, and that's called the range. Now we can actually just scroll up really quick, and this was like the example of the poor automobile was not in the range because there's my only two outputs. The automobile was not hit, but these two outputs are in the range. And so this is a nice example of something which is not onto because there's something in the codomain which is not in the range. On the other hand, there are definitely examples of objects which are onto. I'm not entirely sure, but I'm fairly certain that that function would be an onto function, because if you looked at the range of that function, you'd have to plot it to find out, but more or less the plot would probably do something like that. And then you would see that the entire up-down part of the axis is met, which would make it onto. But that's what you want to think with the range and the codomain. If they're equal, then you have this thing called surjectivity, and then finally you have something called bijectivity, also known as invertible. So these are the same meaning too, and this is when the function is both injective and surjective. So if you satisfy both of the above, two objects end up in the same place, they must have started in the same place, as well as the codomain and range being equal, you have a function that's called bijective. Finally, we do have one more term, which is the composition of functions. And this one's not too crazy because you were using it in calculus for sure. The chain rule requires that you know what function composition is. This is where if the codomain of f and the domain of g are the same set, then you can define g circle of f, or really what we say is g composed with f. That is a function, so I'm going to denote it like a function with a colon and say I map the domain of f, now that's a set, right, to the codomain of g, also a set. And now there's my domain codomain part of me defining a function. I can also define this off of its input as a rule, right? The rule is that I take f, I act it on the input x, right? There's my input, I act f on x, and then I act g on f on x. So that's called a composition of functions. And it's been a long day. I don't want to give you too much to think about. So we're going to stop there before I get into too many examples of these injective and surjective and bijective and compositions of functions. That's really what we'll spend the next class period on. I'll see you then. Bye.